The same thing when they told me about it.
Yeah, I was quoting you.
Oh, okay.
Actually, it will be a very hard job flying.
Anybody needing audio? It's just slideshows?
There's just slides.
Okay, we're all set. Good.
I'm just curious about the slide. Basically what you're looking at.
You're the slider.
He's the button pusher. Every group has a button.
Okay.
And I
Will there be singing and dancing?
God, I hope not.
Can't say.
I was just worrying about the talking. So are we on the clock now?
Yeah.
Okay, cool. Hi, I'm Mike Ravine, for those of you who hadn't sat through one of these before. I'm from Mail and Space Science Systems. I'm the Advanced Project Manager, which means mostly I do new business development and manage our flight development projects. If you happen to be here last year, you heard me talk about two missions that we were on both of, and NASA made the selection, so I'm going to talk about the one mission that's actually now a real mission, not a potential mission. And much to everybody's surprise, they picked the mission that everybody seemed, in my recollection anyway last year, everybody seemed to think the coolest one, which is a mission called Dragonfly, which will fly a nuclear-powered drone on Titan, Saturn's largest moons. And on the panel, I also have Dr. Benford of UC Irvine, who will, I think, ask me questions I probably won't be able to answer.
I'm the official skeptic. Expect sarcasm and irony. Irony is excellent.
You were actually doing work there.
Yeah.
So, something that'll be a recurring theme with this, Titan has an atmosphere, which is how you can fly there. Titan has a very thick atmosphere, and it's an atmosphere that's not very clear in the visible. You can see a little bit of texture through here, and it turns out that's where Dragonfly is actually going to land. A little bit of background first. Dragonfly is going to be a mission that's part of the NASA New Frontiers program. This is a program to do billion-dollar missions that are proposed by individual principal investigators. And just as a point of reference, Dragonfly will be the fourth New Frontiers mission. The first New Frontier mission was New Horizons, which flew by Pluto and a Kuiper Belt object. I was on a competing proposal that lost, so I don't want to talk about that at all. The second New Frontiers mission was Juno, which we have a camera on and took that awesome picture, so that's still operating Jupiter. The third New Frontiers mission was the OSIRIS-REx asteroid sample return mission, which is just getting ready to collect its sample at OSIRIS-REx and bring it back. We have cameras on that, the one who took that picture. Go to the next one. So, New Frontiers 4 selected Dragonfly over the Comet sample return mission I talked about last year. So just to give you some background, oh yes, Dragonfly doesn't stand for anything. Did I have a stroke or something?
This is fine.
You want it lighter?
No, it's, I'll keep talking. Anyway, Dragonfly doesn't stand for anything. The principal investigator, Elizabeth Turtle from the Johns Hopkins Applied Physics Lab, I guess just like the name or something because it flies. So what we're talking about, just to give you context, this is all more or less to scale except for the smaller moons. Saturn has some ridiculous number of moons, like 62 or something like that. Titan is the largest. Titan's quite big, much bigger than the rest of the moons, and as I said, has an atmosphere, but that's sort of the size of Saturn compared to it. And Titan is, almost as big as Mars. This shows Venus, Earth, Mars, Titan, Mercury, the Moon, and Pluto. So the fact that it has an atmosphere is, I understand. It actually has the second highest surface pressure of any body. It's a higher surface pressure than the Earth. It just doesn't have high surface pressure as Venus. It has a surface gravity about like that of the Moon, about 1/6 or 1/7 of Earth's.
All right, leave it there.
That's great.
And
That's
go
great.
sit.
Thank you. If you go to the next one. So these are the statistics that I won't read because they're all boring, but like I said, it's about like the Moon. The surface pressure is about 1.5 times the surface pressure on Earth. Because it's so cold, the density is actually much higher. It's more like 4 times the density of the air in this room, which you might imagine will have something to do with facilitating flying. There's more atmosphere to push on. And the surface temperature is 94 Kelvin, which is 294 degrees Fahrenheit
Minus.
below zero. And the surface that you see and will land on the bedrock there is water ice. Much deeper down is rock. See if I can do this. As I said, the atmosphere is quite. The atmosphere is quite thick, and so if you were to, take a visible image of Titan, it looks like that. If you take images through a narrowband filter in the near infrared, you can actually apparently have no idea what I'm doing. Is the problem. Okay, if you just kind of like flicker back and forth. Anyway, if you look through a narrowband filter, you can actually see surface texture that's going on here. So that's actually interesting. So we know there's things down there. It's not just a featureless ball. Go to the next one. And a little background context. We have sent a number of missions to the Saturn area before, starting with Pioneer 11 and the 2 Voyagers. Those were all flybys. And then there was the Cassini mission, which was an orbiter. And Cassini also orbited for quite a long time, and just recently crashed it into Saturn. Cassini also carried a probe built by the European Space Agency called Huygens, which actually landed on the surface of Titan and took a picture, which I'll show you in just a second. A great picture, but it is a picture of the surface of Titan, so we have some idea what it looks like. Next one. And as I said, it's water. It's solid ice on the outside. We believe it's liquid water underneath, and then rock down farther. There were enough flybys of Cassini, of Titan, Titan that we could take these narrowband images and make them in a global mosaic. So this is all of Titan. It's like some things are light and some things are dark. And if you look really closely, you can see a few craters in some places. We also had, if you go to the next one, Cassini had a radar on it, and so it shot these little swaths that are much higher resolution than we can get with the visible imaging system. And what we learned from this, go to the next one, the purple stuff here are actually sand dunes, and the blue stuff, there's a little bit here, and most of its polar areas are actually lakes, and they're Great Lakes-sized lakes. They're based on chemical thermodynamic arguments. They're probably some combination of methane and ethane, but covering many, many thousands of square miles. We worked on a proposal about 10 years ago to land a boat on one of those, but that was a little bit out there. It didn't get selected, so somehow something that's going to fly is a better bet. I still don't understand that. Anyway, so the interesting thing about Titan is that it's completely different. It's hundreds of degrees below zero. The atmosphere is methane. The seas are ethane and methane. But in terms of the geomorphology, it actually looks very similar to Earth. So it would be this completely alien environment with all these different similarities. So if you go to the next one, Roger. There are craters everywhere. Not very many craters, which tell you it's geologically pretty active because the craters have been obliterated mostly, but there's a few, and we're actually going to land Dragonfly near one of them. Go to the next one. Something that nobody predicted was that a lot of the surface of Titan is covered by dunes. Now, the belief is that the dunes, it was initially thought the dunes would be made up of sand grains that were water ice grains, but it turns out that doesn't actually work. The belief is the particles in the dunes are hydrocarbons that precipitate out at high level and aggregate together, and they land on the ground, and then they form up in dunes. So there's actually more dunes on Titan than on any other planet in the solar system. Go to the next one.
Question.
Yeah.
So if there are dunes, is there wind on Titan?
Oh yeah. Got to have wind to have dunes. Yeah. No, not apparently not really violent wind, but definitely enough wind to loft these particles, making the dunes. As I was saying, there are also these lakes, and they're actually pretty big, like I said, hundreds of kilometers across. You got lakes, you got rivers cutting channels, doing erosion. So again, morphologies that are very similar to Earth, even though all of the materials are completely different and the temperatures are completely different. And so globally, On Titan, there's a methane cycle like there's a water cycle. They taught you in science class when you were a kid. Clouds, weather systems, there is precipitation, so it does rain. That's how we get those dendritic kind of river valleys. So many, many interesting things to see.
It's not tide locked, is it?
It is.
Oh, it is tide.
It is Titan. So the day on Titan is like 2 weeks long.
Right.
And that'll feed back into the whole operations thing you were asking about.
So in other words, so Titan always keeps the same face towards
Yeah. Like I said, part of the Cassini mission was the European Space Agency Huygens probe, this is a cartoon of it landing. The primary focus of it was to make a lot of measurements of the atmosphere. Again, we proposed a camera for this, but they didn't pick our camera, and everybody got a lot better pictures if they picked our camera. Anyway, but what we do have is it landed and it had a very narrow field of view that was oriented upwards, and then it didn't move and it couldn't scan, so it sent this picture back like, I don't know, 100 times or something like that. So what you're looking at here is the ground right up against the probe, and then you're sort of seeing this go off into the distance all the way up to the horizon, sort of like, that kind of perspective if you think about, the surface of the moon. So certainly learned things from this. One is you have a bunch of rocks here. You notice the rocks are rounded, which is what you get when you have rocks that are transported into fluid, they bang into each other and they get rounded. So that's clearly one of those, there's rivers operating around here forming this landform here.
There's hydrocarbons on it?
Probably water ice rocks being transported by liquid ethane, methane mixture. Next one. I just had to put this one in because this is really cool. The whole thing about there being lakes on Titan, it made sense thermodynamically, but not having observed them, it's like, yeah, well, maybe that's kind of out there, whatever. So we started getting some indication there were these dark areas in these pictures. It's like, well, is this really, a liquid surface? Well, it turns out Cassini managed to get this glancing shot where you're actually seeing sunlight bounce off the surface of one of these lakes and come up. That's what that little glint is there. So I just thought that was a pretty cool picture. So actually, go back.
Sorry.
I didn't have a chance to read it. So from a scientific standpoint, besides the fact that this is going to be really cool, we're supposed to have scientific reasons for doing this. An interesting thing about Titan, when Earth originally formed life, the conditions were very different, and those conditions have more or less been completely obliterated by what life has done to Earth since then, and also some evolution of things on Earth. One of the motivations for going to Titan is probably sort of captures the chemistry, something much more representative of the chemistry of what the Earth was like after things were cool enough for interesting chemistry to go on, because there hasn't really been that kind of development on Titan since then. So this is a way to get some handle on the sort of prebiotic part of the origin of life story, in addition to all the other cool things I talked about, like geomorphology and just general exploration. So I think that the next one just sort of recapitulates. Yeah, so the prebiotic chemistry part. This one I was kind of found it a bit of a stretch because NASA likes to talk about habitable environments. That way they don't have to take responsibility for actually saying they're looking for life. They're looking for a place where life could arise. And nobody's really thinking there's any life on Titan right now because it's too cold, and I don't think anybody has much belief that it's likely that there's going to be any chemistry going on at 300 degrees below zero. But it is a complex system with fluids, a cycle, input from the sun, input from tidal forces from Saturn. So we think that there's analogies there that would teach us something about how things came up on Earth. And likewise, it's not just that it's chemistry, it's actually hydrocarbon-based chemistry, so there's a lot of reasons why chemistry that's interesting.
What's the surface temperature again?
94K,
Yeah, that's what I thought.
not quite liquid nitrogen, but pretty close.
Yep.
Liquid nitrogen 77.
So it is actually this is where the I was describing where the sand grains come from. It's like horrific smog actually, and there's photochemistry that happens up high, forming organics, and they clump together, and eventually they get large enough and heavy enough that they can settle out on the ground and then be transported by the wind to form up in those particular kind of sand dunes. So that's the background stuff. The vehicle we're talking about, the joke that Dr. Benford made, I got a call from a guy I know at Johns Hopkins Applied Physics Lab a couple of years ago saying, we're working on this mission and we need some cameras, are you interested? And I said, well, what's the mission? And he said, well, what you do is you take the Curiosity rover and you take the wheels off and you put skids on and you put propellers on and then it'll fly. And I said, that'll never fly. Because I mean, this thing, I mean, it's the size of a, like a Mini Cooper, and then it's got the giant, block of plutonium on the back end. And just like, well, that's not going to fly. And he said, it's 1.6 G and 1.5 bar surface pressure. It'll fly. And I thought, yeah, okay. I guess maybe it could. So you got more, less gravity, so you have to push less hard, and you got more atmosphere to push on. It turns out that the flow regime in this is something that actually can be reasonably simulated on Earth. I mean, you can simulate the cold. You haven't simulated the cold yet, but in terms of how much thrust you need and the power, that's something done. They've already built test drones to do this. So the aerodynamics of it look reasonably solid. So, like I said, it's got the 50 kilograms of plutonium-238 in the back, because certainly Saturn is 10 times farther from the sun than the Earth is, so there's a 1/100th of solar power available, and then there's the thick clouds, so solar power would never work there. We can communicate direct to Earth with this big phased array antenna. We will take images, well, we take mostly images, but other measurements during flight, so the operational scenario, yeah, go to the next one. So before I get to that, this is the thing that'll be flying around on Titan. It's got to go in a heat shield, and there'll be a parachute, and then there'll be a carrier spacecraft. So for the 8 years it takes to get to Titan, it's going to be in deep space looking like that. It'll drop it in, and the whole entry system is very similar to what was used in Curiosity and what we used on the Perseverance rover next year when it gets to Mars.
What's the landing though? You gotta use chutes or just a rocket?
I have a video of that. So
That's called a lead.
people like to thank you, and I appreciate that too.
Mike, one quick technical question. Since the atmospheric density is different than on Earth, do the rotors have to have a different shape because they're operating different Reynolds number?
There is definitely some optimization about that, yeah. And the people on our team are actually some aeronautic guys at Penn State.
Nice.
They're doing a huge amount of R&D on that as part of this.
I just worked out the lifting equation, and it looks as though you could fly it at 1/5 of the velocity you would need on the Earth for the same lifting factor. So 1/5, that's pretty good.
Yeah.
So what's the power of the plutonium?
It's less than a kilowatt. I think it's maybe
And
500 watts.
The mass is how many tons?
So I don't have it 600 to 800 kilograms.
Okay.
The whole vehicle.
The whole flyer, the Dragonfly is how many kilograms?
600 to 800, something like that.
Okay, half a ton.
Yeah.
Okay, then, okay, you're gonna need that factor of 1/5, because that little power, I mean, that's the marginal end of
Well,
a
sorry.
single wing plane.
If we're going to get into this level of detail, like
I just worked it out.
there's another piece of information you're lacking, however, which
Yeah, it's
is
the airport,
which is
the wings.
the power balance is such that it's not like you could fly forever
No.
on the output of the RTG. So it has a whole bunch of batteries.
Right.
So the way flight works is
Right.
it sits on the ground for a week, charging up the batteries, and then it takes like, an hour flight, and it sits down, it's gotta charge up a week again.
Yeah. Did you calculate what the mean temperature is gonna be? Because the plutonium is gonna warm it up some, but it's surrounded by something at 90 Kelvin. It's gotta be really
Well,
happy functioning, very cold.
For other applications, they usually refer to the heat that comes off the RTG as waste heat, but in this particular case, there's a whole heat pipe system.
Right.
I mean, you can see this on Curiosity, there are giant heat fins here to get rid of the heat. This is all insulation here because the heat's being routed inside to keep it, so it's actually a real benefit to, and all of this is fairly thick insulation.
So you don't have to have the electronics that will survive that?
Well, that was the second thing when Ralph Lorenz called me up. I said, yeah, we're interested. Okay, it'll fly. What you want to do, they got to build the thing. So they got to build the thing to work when it's really cold on Titan. That's a problem they have to solve. It's like, we don't build cameras that work at liquid nitrogen temperatures. So I said, so you're going to give us a window and a place where it's reasonably warm to look out of, and that's how it's going to work. And then you have to pay us a bunch of money to develop new cameras that work at liquid nitrogen temperatures. He said, yeah. So we don't have to deal with that problem.
How long did the lander last?
Excuse me?
How long did the lander
Oh,
survive?
it was battery powered, so it lasted a few hours.
Yeah.
Yeah. So more bang for your buck. Yeah. Go to the next one. Yeah. So yes, we take 8 years to get to Titan. So it'd be better if we had better rockets, but I look forward to that someday. And we'll have to fly by Earth and Venus a couple of times for some gravity assist maneuvers. Eventually we'll get to Titan. We come in with the heat shield. We come in, we get rid of the cruise stage, enter the atmosphere, slow down a whole bunch, deploy a parachute, swing on the parachute for a while, drop the parachute, drop the heat shield, separate from the back shell, fire up the props, and then we're in business.
What's the launch vehicle?
Well, I don't think that's been decided. I believe it can go on an Atlas, but
Why not use the BFR? It'll be there.
well, I hope it is there, but the planning horizon on NASA is long enough. Well, for the Psyche mission that we have cameras on, they just announced this month they're going to use the Falcon Heavy, so they have gotten over the idea that they can contract with SpaceX to do these missions, and so if it ended up going on Falcon Heavy, I wouldn't be surprised that BFR might be overkill.
Yeah, well, but you could cut out all this flyby stuff and get it there years earlier.
Yeah, again, the planning cycle is such that, they have to have this plan, they're gonna do this plan, it's.
So you can change the trajectory at the last minute.
What is BFR, by the way?
Oh, that's, Big Falcon rocket.
Okay.
We're wondering about that F.
I think that's where they ended up. If you go to the next one. Okay, now we came to the video. So this is showing it on the parachute that the heat shield's been dropped, so the skids deploy, and then it drops out, and they start the props. I think they start the props after it separates,
Oh, and it lands itself.
and it lands itself.
Wow.
Because it's got to be able to land itself. So
Might as well start the way you plan to continue. Yeah.
You gotta get a very low velocity descent in order to make that work. So, yeah.
yeah. So then it puts up the high gain antenna. And it turns out that these two things on the high gain antenna are two of our cameras that are meant to shoot panoramas. That way they only had to have one scan mechanism to be able to do that rather than two. And then it takes off and heads to the next site.
And you said it takes about a week to recharge the batteries, so about a week at each site?
Well, there's a cadence here that's mostly driven by the day-night cycle on Titan, which is 7 days sun up, 7 days sun down. The idea would be one target per week. Charge overnight, do the flying in the morning, land, do the 10 days worth of science while you're charging the batteries, and then do the next thing. The one clever thing they did, and it's not really shown here, the one-way light time to Saturn is like more than an hour, so it's not like there's going to be anybody flying this with ground in the loop. So the vehicle has to fly itself. And that requires a certain amount of smarts. It turns out it doesn't have to be too smart, because the way the operations will work is that on a given day, it will take off and it will fly a couple miles downrange, and then and taking pictures all along the way, and then it will turn around and fly about halfway back and land at a point that was picked based on the images taken the day before. And then it will send down those images, which will include a mile ahead of it, and based on those images, people on the ground will say, we want to land here, and it will tell the vehicle to land there the next day. So the vehicle has to be able to fly itself and remain stable and know where the ground is and land. But what the vehicle doesn't have to do is it doesn't have to be smart enough to pick a good landing site. That will be done by people on the ground. And since I think that's the hardest problem from a computer standpoint.
Can it land in the dark? It's using down radar, so I guess it could.
Well, all I know is that most of what they're talking about doing, imaging, is playing a pretty critical role. So I think they're not planning on it landing in the dark. The dark is just going to be for sitting there and charging the batteries and making measurements like the seismometry and stuff like that don't require sunlight. So the plan is to land here. This is a dune field south of one of the craters. It's called Selt Crater. And the idea will be we'll land in here in this dune field, and then we'll be hopping north and north out of the dune field into this crater ejecta, and eventually potentially down into the crater to sample some other things. It turns out this particular area was a place where we could go. We're not going to a lake, but we're sort of sampling all the other representative terrains of Titans. This was a particularly appropriate place to go. In the nominal mission, we expect to go through 24 of these Titan day-long cycles where we take off and land and take data. So that'd be 24 sites. As with most of these things, we hope that it lasts a lot longer than that, and we get a lot more mileage out of that. But that certainly would be worth doing.
Could it land in a very shallow pool?
I guess the question would be, how would you know what the depth was?
Ground down radar.
Yeah. I haven't asked that question.
And it's probably too late in the design process to put pontoons in.
Yeah, I don't know, that would be, I'm also worried about where the CG is.
Yeah.
I think, I'm not sure that would work. Go to the next one. So, there are a whole bunch of instruments on, which I will mention briefly, except for the cameras, because we're building the cameras, so I can talk about that all day. There's a mass spectrometer, which will measure the elemental and molecular composition of the Titan atmosphere, and also samples that will be drawn up from the surface by sample collection system, which is this drill system, and then a sort of organic system that will vacuum up the particulates and bring them up to the mass spectrometer. There's a gamma ray neutron spectrometer, which will give us compositional elemental information about the composition about a meter down below the surface. There's an atmosphere, so there's a meteorology package. And then finally there's cameras. Actually, it turns out we have 10 cameras on the rover. So 10. Wow. So first you have to divide that by 2, because this is a big mission. It has full redundancy, so we have 2 each of 5 different kinds of cameras. So there are 2 cameras. Actually, if you could go back to the picture there. We have 2 cameras in the front that are actually that talk directly to the rover computer and are used in real time for flying the rover. Sorry, vehicle, whatever, drone. On the bottom, there are 2 cameras whose purpose is basically to look down, both when we're up high, we're taking images during descent, or when we're flying along this traverse to pick out the next landing site. And when we're on the ground, to take pictures of what they call the workspace, the area where we're collecting the sample from. There are 2 cameras that actually have a focus mechanism that are to take high resolution pictures to actually see individual grain size in the little area where we're doing the drilling and collecting the sample. And then there are 2 cameras on the high gain antenna for doing the panoramic imaging.
Are they movable?
Yeah, the purpose of putting them on the high gain is the high gain had to be movable, be pointable, and they didn't want to add a whole separate remote sensing mast like they have on MSL, so we're just stuck on there. Those are actually as you might imagine, thermally the hardest things, because those are actually outside of the main rover body. So,
So they gotta freeze.
they're gonna get cold and they have to burn a bunch of power, and actually there's little, you don't see it in this rendering, but when they fold it down, those goes into sort of little alcoves in the top of the vehicle to help keep them warm.
Do you know the plutonium mass?
I keep throwing around this number of like 50-some kilograms, but if I were actually putting a bet down, I would probably go look it up again, but that number,
Well, that's about this much.
yeah, it's not very much.
Really dense.
Are
But
the
heavy.
two top cameras for stereoscopic view, or are they different, do different things?
They're two duplicate copies of the camera, so it's for redundancy, but since they're offset, it will also be, as long as they're both working, it'll also be good for stereo, yeah. Yeah, and I think this is one of my, corporate rah-rah things, they had a lot of challenges with this, and the reason they came to us for these cameras is basically, they didn't want the cameras to be part of the challenge of the mission. They just wanted us to give cameras that we already knew how to build, and so that's what we offered them. So these are just pictures of other cameras that we've flown that we're basically gonna make into these cameras we need for this mission, so.
What operating temperature do they need?
The cameras?
Yeah.
Well, we like them not to be below like minus 40
Minus 40 C?
C, yeah, sorry.
You're gonna keep them that warm? But it's surrounded by minus 270?
Well, but they're having to keep the inside of the vehicle fairly
Right.
warm. But the other thing is that when we're not on, the cameras can go down to minus 135.
Oh.
So it will be one of those heat to use kind of situations where when they want to use them, there'll be specific dedicated heaters in the cameras. We'll warm them up to the temperature range, and then
And it won't kill your chips? That temperature?
we. We had to build cameras that would survive down to minus 135 for curiosity.
Oh, yeah.
These are different cameras, and so we're going to have to go through a whole new qualification process. But for curiosity, we built one of these boards, and we put it in a thermal chamber, and we cycled it down to minus 135 2,000 times to prove that it could take it, so we're going to do something similar. to
These
this.
are all charge coupled detectors, right?
These are actually CMOS detectors, because they've stopped making CCDs. They're on their way out, and so we're having to figure out how to use CMOS detectors. And in this particular case, the reason it's only minus 40 is these are actually commercial parts that we have upscreened for flight applications.
This is off the shelf.
The parts are off the shelf, but then we do a whole bunch of testing to prove that they'll be good.